A world of solid diamond orbits a distant sun. This is not science fiction, but a real scientific hypothesis about an exoplanet called 55 Cancri e, a carbon-rich super-Earth. By the end of this exploration, you will understand how astronomers discovered this cosmic jewel and what its hellish existence reveals about the universe's strangest planets. We will investigate how a star's unusual recipe could forge a diamond core and what searing temperatures do to a world made of precious gemstone. What does the possibility of such extreme wealth in the cosmos make you wonder about our place in it all? In 2004, a team of astronomers made a remarkable announcement. They had found a new world, not with a telescope's eye, but by feeling the subtle wobble of a distant star. This was the discovery of 55 Cancri e, detected using the radial velocity method. The principle is elegant in its simplicity. As a planet orbits its star, its gravity tugs on the star, causing the star to move in a tiny, rhythmic dance. From our vantage point, this motion shifts the star's light ever so slightly toward the blue and then the red part of the spectrum. By meticulously measuring this stellar wobble, scientists can infer the presence of an unseen planet, its mass, and the length of its year. The planet they found orbits a sun-like star called 55 Cancri a star visible in the constellation of Cancer on a clear, dark night. But this is no simple solar system. 55 Cancri a is part of a binary pair, with a smaller red dwarf star orbiting far out on the fringes. Finding a planet in such a multi-star system added a fascinating layer of complexity to the discovery. It proved that planets could form and persist even in the gravitational tug of war between two stars. The data revealed a world of startling proportions. 55 Cancri e was classified as a super-Earth, but that term can be misleading. It simply means it is larger than our home planet but smaller than the gas giants like Neptune. In this case, the measurements were staggering. This new world was calculated to be roughly twice the diameter of Earth, yet it packed over 8 times Earth's mass into that volume. That incredible density was the first major clue that 55 Cancri e was no rocky world like our own. Something exotic, something far denser, had to be making up its bulk. The search for an answer to that mystery would begin to point toward a truly glittering possibility. The planet's staggering density was a puzzle, but the solution lay not just in the world itself, but in the star it called home. To understand 55 Cancri e, astronomers had to first decipher the recipe of its sun, 55 Cancri a. They did this using a powerful technique called stellar spectroscopy. Imagine starlight not just as a white beam, but as a cosmic barcode. When that light passes through a spectrograph, it gets stretched into a full rainbow, a spectrum. Etched across that rainbow are dark lines like unique fingerprints. Each element in the star's outer layers absorbs specific colors of light, creating these telltale gaps. By reading this barcode, scientists can count the atoms. They can measure how much iron, silicon, oxygen, and carbon are burning in that distant furnace. What they found was a profound anomaly. Our sun is an oxygen-rich star. For every carbon atom in its atmosphere, there are roughly 2 oxygen atoms. This oxygen-heavy chemistry is the foundation of our rocky solar system, giving us a world built on silicates and water. But 55 Cancri told a different story. Its barcode revealed a much higher ratio of carbon to oxygen. In this system, carbon was the dominant element. This was the first monumental clue. If the star is carbon-rich, then the cloud of dust and gas that collapsed to form it, the very raw material for its planets, must have been carbon-rich as well. It's like a cosmic chef starting with a pantry full of sugar instead of flour. The cakes you bake from it will have a fundamentally different structure. A planet forming in such a carbon-saturated environment would not be built from the rocky, oxygen-based minerals we know. Instead, its very core could be forged from something far more exotic, something that forms under immense pressure when carbon is abundant. The stage was now set for a radical reimagining of what 55 Cancri E might truly be. With a carbon-rich star identified, the stage was set for a revolutionary idea. Between 2010 and 2012, a series of groundbreaking studies led by researchers like Niku Madhusudhan dared to ask a stunning question. What if 55 Cancri E was not just a dense super-Earth, but an entirely new class of world? They proposed the carbon planet hypothesis. The logic was compelling. In a stellar system where carbon atoms outnumber oxygen atoms, the chemistry of planet formation flips completely. Think of it like this. In our solar system, with its oxygen abundance, the fundamental building blocks of planets are silicates, compounds of silicon and oxygen. These are the common rocks and minerals of Earth, but in the 55 Cancri system, the dominant available elements are different. Here, carbon would eagerly bond with other available elements, creating an exotic foundation. Instead of a mantle of silicate rock, a planet like 55 Cancri E could be built from substances like graphite, the soft, dark material in your pencil, and silicon carbide, an incredibly hard ceramic. This alone would explain the planet's unusual density, yet the model went even further into the realm of the spectacular. Deep within such a world, under the crushing pressure of thousands of miles of overlying material, those carbon compounds would be subjected to forces beyond our everyday experience. Graphite, when squeezed and heated under these extreme planetary conditions, undergoes a profound transformation. Its atomic structure rearranges, locking into an immensely strong, rigid lattice. It crystallizes, and what is the crystalline form of pure carbon, diamond? The hypothesis suggested that a significant portion of this planet's interior, its very core, could be a solid mass of diamond. Not a few sparkling gems, but a layer potentially thousands of miles thick, a glittering geological stratum forged in the furnace of a young star system. This was no longer just an exoplanet, it was a cosmic jewel, a testament to the universe's capacity for creating wonders far stranger than fiction. But how could we ever confirm such a dazzling idea from light years away? The Diamond Planet is a world of unimaginable extremes. Its orbit is so tight that a single year, one full trip around its star, lasts less than 18 hours. To stand on its surface, if such a thing were possible, would be to witness a sun that dominates the entire sky, a blazing disk of fire so close you could almost reach out and touch it. This proximity creates a furnace. Current estimates suggest the dayside surface temperature could soar beyond 2,000 degrees Celsius, hot enough to melt iron and vaporize rock. This is not a landscape of mountains and valleys as we know them, but a searing hellscape where the very ground might be a global ocean of molten silicate lava, constantly churning under the star's relentless glare. But the strangeness deepens with a phenomenon called tidal locking. Just as our moon always shows the same face to Earth, 55 Cancri E is likely locked to its star. One hemisphere, the day side, is perpetually cooked in that brutal, unwavering sunlight. The other hemisphere, the night side, is forever turned away into the freezing blackness of space. This creates the ultimate planetary contrast. The day side could be a single, incandescent sea of lava. The night side, however, is a different story. Shielded from the star's fury, temperatures there would plummet. This is where the planet's proposed carbon-rich nature becomes eerily tangible. On that permanent night, the atmosphere itself might freeze out, falling as strange carbon-based snow. And the surface, no longer molten, could solidify into a dark, brittle crust of graphite, or even, in the profound cold and stillness, into vast, dark plains of crystalline structure. So this world of incredible wealth is also a world of impossible duality. One face a roiling ocean of fire, the other a frozen, silent wasteland of carbon, with a heart of diamond beating deep below it all. A planet of diamond is a breathtaking idea, but science demands more than a beautiful hypothesis. It requires evidence, and the evidence for 55 Cancri E began to mount from an unexpected direction: its light. The Spitzer space telescope, an infrared observatory, played a pivotal role. It didn't take a picture of the planet, but it could sense its heat. As 55 Cancri E passed behind its star, a phenomenon called a secondary eclipse, astronomers used Spitzer to measure the tiny dip in the total infrared light from the system. This allowed them to calculate the planet's own thermal emission, the heat radiating from its blistering surface. The readings were extreme and uneven, showing a massive temperature difference between the scorching day side and the frigid night side. This confirmed the tidal locking and suggested a startling possibility. The planet had little to no atmosphere to redistribute that heat. A substantial atmosphere, like Venus's thick blanket, would smooth out those temperature extremes. The absence of one pointed toward a world where volatile gases like water vapor or carbon dioxide could not survive the star's intense radiation. This fit the carbon planet model perfectly. A world built from refractory materials like graphite and silicon carbide, substances that remain stable under incredible heat, would not hold onto a fluffy atmosphere. Later observations from the Hubble Space Telescope searched for the spectroscopic fingerprints of an atmosphere and came up largely empty, further strengthening the case for a bare, exotic surface. The most compelling data, however, came from simply weighing and measuring the world. Refined observations of its transit and its star's wobble gave astronomers its radius and mass with remarkable precision. When you know a planet's size and its mass, you can calculate its density. The density of 55 Cancri E is about twice that of Earth. This number is a crucial clue. A water world, even a steamy super-Earth, would be much less dense. A rocky, Earth-like world of silicates and an iron core cannot explain that high a density either. The only plausible models that match the numbers involve a huge amount of carbon in the form of dense compounds. Computer simulations of the planet's interior consistently showed that to achieve that density, a significant fraction of its mass, potentially a third, must be carbon. And under the pressures found thousands of miles deep in a super-Earth, that carbon inevitably crystallizes. The diamond interior ceased to be just a speculative idea. It became the most elegant solution to a hard set of physical measurements. Each new telescope, from the European Space Agency's CHEOPS to the mighty James Webb, has turned its gaze toward this world, not to find a shimmering jewel in the void, but to read the subtle signatures written in heat and light that tell the story of its impossible composition. The reality of this world defies any postcard image of a glittering sphere in space. Visualizing 55 Cancri E requires blending harsh physics with speculative wonder. On its permanent day side, under the star's furious gaze, the surface is likely a global ocean of incandescent lava. But this is not the familiar basaltic lava of Earth's volcanoes. In a carbon-rich system, this molten sea could be a bizarre metallic soup, thick with dissolved carbon and silicates, shimmering with temperatures that vaporize stone. It might glow with a sickly yellow or orange hue, constantly churning under tidal forces and stellar winds. Any mountains that attempted to rise would be swiftly melted back into this seething global furnace. Yet, as we move toward the terminator, the line between eternal day and endless night, the landscape would transform. Here, temperatures plunge rapidly. The lava would solidify into a dark, brittle crust. This is where the planet's exotic chemistry becomes its geology. The surface could be a vast, desolate plain of graphite, the same soft, slippery carbon in your pencil lead, but forged on a planetary scale. Scattered across this dark plain might be jagged, glassy outcrops of silicon carbide, a material so hard it's used industrially as an abrasive. These would be the mountains of this world, not uplifted by tectonic plates, but perhaps crystallized from the cooling melt or exposed by eons of stellar erosion. Their facets might catch the dim, reflected glow from the lava side, glinting with a dull, metallic sheen, but the true spectacle lies buried. Beneath this strange surface, pressures mount exponentially. Within a few hundred kilometers down, the crushing weight of the planet itself would force the atomic structure of carbon to rearrange. The graphite would undergo a profound metamorphosis. Its atoms would lock into that iconic, incredibly strong lattice. This transition zone might create a geological stratum unlike any in our solar system, a diamondiferous layer, a mix of diamond crystals forming within the surrounding matrix. Deeper still, perhaps 1,000 kilometers down, the pressure becomes so immense that this mixture could give way to a pure, continuous stratum. Imagine not a single gem, but a geological ocean of solid diamond, hundreds or even thousands of kilometers thick. It would be a crystal of planetary scale, its facets measured in continents, its clarity obscured by the immense pressures and trapped impurities. There would be no sparkle, no brilliant refraction of light, only a dark, super-dense and impossibly hard heart. So the diamond planet is not a shiny bauble. It is a world of violent duality, one face a storm of liquid fire, the other a frozen carbon desert, all anchored to a core of the universe's most precious stone. What could possibly shape such a world into being, and does its existence hint at others like it hiding in the galactic dark? How could a world with a diamond heart even come to exist? Its formation is a cosmic detective story with two compelling and equally dramatic suspects. The first theory begins far from the star's blistering heat. In the young 55 Cancri system, the protoplanetary disk was not a uniform cloud. It was a cosmic gradient with temperature and chemistry changing dramatically with distance. Close to the infant star, where temperatures were searing, only the most refractory materials could condense into solid dust grains, things like metals and certain silicates. But farther out, in the cooler, darker reaches of the disk, a different kind of chemistry took hold. Here, carbon compounds could solidify. Imagine snowflakes, but instead of water ice, they are flakes of graphite, tar-like hydrocarbons, and other carbon-rich minerals. In this distant, carbon-saturated nursery, 55 Cancri E could have first taken shape as a large, icy rocky body with a stunningly high percentage of carbon in its very blueprint. But it didn't stay out there. Through gravitational interactions with other forming planets or with the gas of the disk itself, this embryonic world could have spiraled inward on a grand migration. As it barreled into the hotter inner system, the volatile ices on its surface would have been blasted away, leaving behind the dense, refractory core of carbon and silicates. What arrived in that hellish orbit near the star was essentially the stripped-down, concentrated heart of a world born in the carbon-rich outer darkness, now ready to be forged into diamond under the new pressures of its scorching home. The second theory is even more cataclysmic. What if 55 Cancri E was not always a super-Earth? What if it began its life as something much larger? In this scenario, the planet started as a gas giant, a mini Neptune, with a relatively small rocky core enveloped by a vast, thick atmosphere of hydrogen and helium. It formed perhaps a bit closer to its star than similar worlds in our system, and that proximity would be its doom. 55 Cancri A, especially in its younger, more violent years, bombarded its close-orbiting planets with intense ultraviolet radiation and powerful stellar winds. Over hundreds of millions of years, this relentless assault could have literally blown away the giant planet's entire gaseous envelope, eroding it layer by layer until nothing was left but its exposed central core. This remnant core would be incredibly dense, and if it formed from carbon-rich material, that core could be the diamond heart we infer today. It's a planetary metamorphosis of staggering violence, the ghost of a gas giant. Its ethereal atmosphere evaporated into space, leaving only its glittering skeleton behind. So, is 55 Cancri a migrant from the cold outer reaches, or the stripped corpse of a former giant? Current data leans toward the migration story, as its density seems more consistent with a primordial carbon-rich world than the mixed debris of a gas giant's core. But the truth is, both pathways are possible in the chaotic forge of a young solar system. They reveal a universe where planets are not fixed in their orbits or their identities, but can undergo radical journeys and transformations, ending up as something utterly unrecognizable from how they began. If such a world can exist, what other impossible-seeming planets might be waiting in the data, and what do they tell us about our own planet's story? This burning question of an atmosphere has proven to be one of the most difficult puzzles to solve. The story of the air around 55 Cancri E is a perfect example of science in motion, where each new observation refines and sometimes overturns what we thought we knew. In the years following its discovery, the initial assumption was that a super-Earth so close to its star would likely be shrouded in a puffy, extended atmosphere of light gases, hydrogen and helium, captured from the primordial stellar nebula. It would be a miniature version of a gas giant, hopelessly bloated and boiling. But as telescopes grew sharper, that simple picture began to dissolve. The extreme temperature difference between the day and night sides, a clue we discussed earlier, was the first major strike against a thick, blanket-like atmosphere. Such an atmosphere would act as a global heating system, efficiently circulating warmth and creating a more uniform temperature across the planet. The fact that one side is infernally hot while the other is cosmically cold strongly suggested the planet was either bare or wrapped in something very tenuous. For a time, the leading theory became that 55 Cancri E was essentially airless, its original atmosphere long ago scorched away by the star's fury, leaving only the searing, naked surface exposed to the void. Yet, nature often defies our cleanest categories. More sensitive observations, particularly those looking at the planet during its transit across the face of its star, began to hint at something more complex. As starlight filters through the very outer fringes of a planet's atmosphere, if one exists, specific gases within that haze can absorb distinct colors of light. Scientists began to search for these minuscule fingerprints in the data. Recent analyses have suggested tantalizing, though not yet definitive, traces of particular molecules. Among them are hydrogen cyanide and carbon monoxide. Now, this sounds alarming, even lethal, and it is, but from a cosmic chemist's perspective, it is utterly fascinating. These are not the molecules of a life-friendly world, but they are the logical products of a carbon-rich one. In an environment dominated by carbon, with intense heat and radiation breaking apart any simple compounds, these are the kinds of molecules that could persist or reform. A thin, transient shroud of such gases could potentially exist, perhaps constantly being boiled off from the molten surface and blasted away by stellar winds in a fragile, dynamic balance. So the atmosphere of 55 Cancri E, if it exists at all, is likely not a stable, global blanket. It might be a wispy, localized haze over the lava ocean, a temporary exhalation of vaporized rock and carbon compounds forever on the edge of being erased. This ongoing detective story reminds us that even the most extreme worlds can hold onto whispers of complexity, and that every answer from our telescopes seems to lead to two new, more intriguing questions. So let's put a price tag on this cosmic jewel. If we assume a third of 55 Cancri E's mass is diamond, we are talking about an amount of carbon that utterly dwarfs human comprehension. The diamond content alone could exceed the mass of our entire planet. Translating that into gemstone terms, the estimates become almost comically large. The number often thrown around is $260 nonillion. That's a 2 followed by 30 zeros. It is a sum so vast it could buy a galaxy if galaxies were for sale. It makes every economy on Earth, every stock market, every vault of gold look like pocket change. This is the trillion, or rather the nonillion dollar question. What would such wealth mean? The answer is simple: absolutely nothing. This calculation is a delightful exercise in cosmic scale, but it is ultimately meaningless, and understanding why reveals something profound about value itself. First and most practically, mining 55 Cancri is pure fantasy. The journey alone would take hundreds of thousands of years with our current technology. Even if we could get there, the environment is a deal breaker. You would need machinery that could operate while submerged in a global lava ocean under crushing gravity and bathed in lethal radiation, all to extract a material that, under those conditions, is just another rock. The engineering challenge is so far beyond impossible it becomes a philosophical point, but the second reason is more fundamental. Diamonds are precious on Earth for one primary reason: scarcity. Their value is a story we have constructed, a narrative of rarity and desire. On a world made of the stuff, diamond loses all special status. It becomes the bedrock, the common stone, the planetary filler. It would be like trying to sell sand in the middle of a desert or ice on a glacier. Its value collapses because it is no longer rare. This playful thought experiment, then, isn't really about economics. It's a mirror. It reflects back to us how our human concepts of wealth and value are tiny, local, and fragile. They do not translate to the cosmos. The true worth of 55 Cancri is not in a hypothetical price tag, but in the knowledge it represents. This world is a natural laboratory. By studying it, we are testing the limits of planetary science. It proves that solar systems can have radically different chemical recipes, leading to planets built from substances we would consider exotic or precious. It challenges our definitions and expands our imagination of what is possible. Each new observation is a data point in understanding the diversity of the universe. That knowledge, the pure, unadorned understanding of our place in a cosmos capable of forging diamond worlds, is the real treasure. It is a wealth that cannot be quantified in dollars, but only in the expanding horizon of human discovery. And if one such world exists, it forces us to ask what other impossible-seeming planets, built from elements we can barely conceive, are waiting silently in the starlight. The existence of 55 Cancri fundamentally rewrote the catalogue of possible planets. It proved that solar systems with a carbon-heavy chemistry could exist, and within them, entirely new geological realities could take shape. This discovery ignited a new search, a hunt for other worlds forged from the same exotic blueprint. Are there more diamond planets scattered across the Milky Way? The answer, astronomers suspect, is a resounding yes. The galaxy is home to hundreds of billions of stars, and a significant fraction of them, especially older stars born in the early universe, are likely carbon-rich. If the raw materials are there, the planets must be too. We are simply learning how to see them. One compelling candidate is a world named WST-12b. This is another hot Jupiter, a gas giant orbiting perilously close to its star. Spectroscopic studies have revealed its atmosphere to be overflowing with carbon, with a carbon-to-oxygen ratio even higher than 55 Cancri Sun. This world is so close to its star that it is being actively devoured. Its outer layers stretched into a teardrop shape and pulled into a glowing disk of doomed material. While its immense gravity means it likely has a more traditional layered interior, its profound carbon abundance makes it a key piece of evidence. It shows that the carbon planet phenomenon is not a one-off fluke, but a direct consequence of stellar chemistry. The discovery of 55 Cancri taught astronomers to look beyond the familiar template of our own solar system. Before its identification, we tended to search for planets that looked like home, rocky worlds with iron cores and silicate mantles orbiting at comfortable distances. Now the search parameters have dramatically expanded. When astronomers study the light from a distant star and find that carbon-rich signature, their curiosity is immediately piqued. They know that any planets there will be built from a different periodic table, potentially hosting landscapes of graphite, silicon carbide, and deep layers of crystallized carbon. This has opened up an entire new category of exotic worlds in our theoretical models, from diamond super-Earths to planets with oceans of tar. The galaxy may be filled with such carbon kingdoms, each one a testament to the diverse and often extreme outcomes of cosmic alchemy. Finding them, however, requires us to listen more carefully to the subtle stories written in starlight. The true test of this glittering hypothesis now lies with a new generation of eyes in the sky. Enter the James Webb Space Telescope, an instrument so powerful it is rewriting the rules of exoplanet science. For a world like 55 Cancri e, Webb is not just another telescope, it is the ultimate detective. Its mission is to move beyond inference and gather the direct, forensic evidence that has eluded us for decades. The telescope's extraordinary sensitivity to infrared light, the kind of radiation that heat and molecules emit, makes it perfectly suited to dissect this extreme world. One of its first major programs dedicated to 55 Cancri e is a meticulous thermal mapping campaign. By observing the planet throughout its entire orbit, from the peak of its dayside blaze to the depths of its nightside chill, Webb can construct a temperature map of unprecedented detail. This is not just about getting a more precise number. The exact shape of that temperature curve, how sharply it falls from day to night, will tell us definitively if this world has any atmosphere at all. Even a whisper-thin shroud of gas would leave a specific signature in how the heat is distributed. A bare, airless rock would show an almost instantaneous temperature plunge, while the presence of any atmosphere, no matter how tenuous, would smooth that transition. Webb's data will settle this long-standing debate with authority, but the telescope's most anticipated work is spectroscopic. As 55 Cancri e transits its star, a sliver of starlight will pass through the very fringes of its environment. Webb can capture that filtered light and spread it into an exquisitely detailed spectrum. Within that data, scientists are hunting for the chemical fingerprints of specific molecules. They are not looking for signs of life, but for the markers of a carbon kingdom. The prime suspects are molecules like hydrogen cyanide, carbon monoxide, and acetylene. Detecting an abundance of these compounds would be a smoking gun, direct proof that the planet's atmosphere, or what remains of it, is fundamentally built from carbon, just as the diamond planet model predicts. Furthermore, by analyzing the planet's own thermal glow as it slips behind the star, Webb can probe the composition of its dayside surface. Different materials like molten silicate lava versus a graphite crust emit infrared light in subtly different ways. Webb's precision might allow us to distinguish between these hellish surfaces for the first time. Every photon of light it collects from this distant system is a piece of a puzzle, bringing us closer to answering the ultimate question. Is 55 Cancri e truly a world with a diamond heart? Webb is not merely observing this planet, it is conducting a cosmic interrogation, demanding answers written in the language of heat and molecular bonds. The data now streaming back to Earth holds the power to confirm one of astronomy's most dazzling ideas or send scientists back to the drawing board in search of an even stranger truth. Peering inside a distant world requires a special kind of vision, one built from mathematics, physics, and computer simulations. To construct a model of 55 Cancri e's interior, planetary scientists begin with the few solid facts they possess. They know its mass, a number derived from the star's wobble. They know its radius, measured as it transits across the stellar disk. And they know the chemical makeup of its sun, which tells them the probable ingredients available for planet building. These three numbers are the foundational pillars. From them, scientists can calculate the planet's average density, which is the first major constraint. Any plausible model of the interior must add up to that exact density. Think of it like a cosmic recipe. You have a bowl that must hold a very specific weight. You can only use ingredients you know were in the kitchen, in this case, a carbon-rich blend of elements. and you have to layer them in a way that makes physical sense under immense pressure and heat. The resulting models are our best-informed guesses, and for 55 Cancri E, they paint a portrait of a world with a startlingly familiar, yet profoundly alien anatomy. Most models agree the planet likely possesses a central core, but not of diamond. Deepest down, where pressures are greatest, the heaviest elements would have sunk during formation. This innermost heart is probably a sphere of molten iron and nickel, similar to Earth's own core, though potentially smaller in proportion. It is the anchor, the densest part of the planetary body. Surrounding this metallic heart is the planet's most extraordinary layer, the mantle. On Earth, our mantle is solid rock, a silicate layer that flows over geologic time. On 55 Cancri E, the mantle is where the carbon takes center stage. Under the crushing weight of thousands of miles of overlying material, carbon is forced into its most stable, compact form. This is not a loose collection of gemstones, but a continuous, solid expanse of crystallized carbon. Scientists refer to high-pressure phases, meaning the specific atomic arrangements carbon adopts under these extreme conditions. The dominant phase here is diamond. This mantle could be hundreds, even thousands of kilometers thick, a geological ocean of solid diamond, hot and under inconceivable pressure, behaving more like a viscous solid than a brittle gem. Above this glittering mantle lies the crust, the planet's outermost shell. Here, pressures are lower, allowing carbon to exist in a different form, graphite. This creates a bizarre surface geology. The crust might be a fractured, dark landscape of graphite, interspersed with patches of solidified silicate lava that bubbled up from below. In some models, the intense heat from the star and the interior could even create a global, roiling magma ocean on the surface, with graphite flakes floating atop it like scum on a boiling pot. These layered models are not just artistic speculation. They are rigorous solutions to equations of state, which describe how matter behaves under extreme conditions. By testing millions of virtual planet interiors against the known mass and radius, supercomputers find the structures that fit. The fact that a carbon-rich model with a significant diamond layer consistently provides the best fit for 55 Cancri E is what transforms a dazzling hypothesis into a robust scientific prediction. It reveals a world with a hidden, crystalline heart, a testament to the universe's ability to craft wonders from the simplest of elements under the right, or rather, the most extreme circumstances. The diamond planet's hellish existence is not only due to its star's heat, but also to its star's relentless gravitational pull. Orbiting so incredibly close, 55 Cancri E is locked in a brutal dance of tidal forces. Imagine the star's gravity not as a uniform pull, but as an immense hand that squeezes the planet from all sides, stretching it slightly toward and away from the stellar surface. This constant, asymmetrical tug creates friction deep within the planet's interior. Rock and crystal grind against each other, generating immense heat from the inside out. This process, called tidal heating, is the same phenomenon that keeps the volcanic moons of Jupiter piping hot. For 55 Cancri E, it could be a primary engine for its global lava ocean, supplementing the blistering radiation from above. The planet may be literally cooked from the inside by the very star it orbits, its diamond heart kept hot and pliable by this unceasing gravitational massage. Such an intimate orbit comes with a profound and ominous implication: orbital decay. The same tidal forces that heat the planet also act as a cosmic brake, slowly sapping its orbital energy. With each pass, the planet's path could be imperceptibly shrinking, dooming it to an eventual death spiral into its sun. Astronomers hunt for evidence of this decay by performing exquisitely precise timing of the planet's transits. They measure to the second exactly when the planet begins and ends its journey across the face of the star. Over years and decades, if the orbit is decaying, these transits will occur slightly earlier each time. The interval between eclipses will get shorter by a tiny but measurable amount. It is a race against time in the most literal sense, searching for a change in timing that might only amount to a few seconds over a century. Detecting this would confirm that the diamond planet is not just a temporary wonder, but a world living on borrowed time, destined to be consumed by the furnace that forged it. This adds a tragic, fleeting beauty to its story, a glittering world born from cosmic chaos, now circling ever closer to its own spectacular end. But the diamond planet does not exist in isolation. To truly understand its story, we must zoom out and see the full cosmic neighborhood it calls home. The star 55 Cancri A, the blazing sun that scorches 55 Cancri E, is not alone. It is the primary member of a binary star system. Its companion, 55 Cancri B, is a small, dim red dwarf star. These two stars are separated by a staggering distance, over 1,000 times the span from our Earth to our Sun. From the perspective of a planet orbiting 55 Cancri A, its companion star would appear only as an exceptionally bright point of light in the eternal night, a distant crimson ember in the void. This vast separation is crucial. It means the gravitational influence of the red dwarf is minimal on the inner planetary family, allowing complex systems to form in stable orbits around the primary star. And what a family it is! Orbiting 55 Cancri are not one, but 5 known worlds, making it one of the richest exoplanet systems we have catalogued. The innermost world is, of course, our subject, the searing super-Earth 55 Cancri E. Beyond it lies 55 Cancri B, a hot Jupiter, a giant planet about the size of our own Jupiter but orbiting incredibly close to its star, completing a year in just under 15 days. Farther out still is 55 Cancri C, another gas giant with an orbit of about 44 days. Then we reach 55 Cancri F, a planet roughly half the mass of Saturn, orbiting in what we might call the system's temperate zone, taking about 260 days to circle its sun. Finally, in the cold outer reaches, we find 55 Cancri D, a true behemoth. This world is a gas giant at least 4 times the mass of Jupiter, lumbering along on an orbit that takes over 14 Earth years to complete. This elaborate architecture reveals a solar system of remarkable complexity and diversity, all orbiting a single star in a binary pair. It shows us that planets can form and persist in a wide variety of orbits and sizes, even in systems very different from our own. The presence of that distant, massive gas giant, 55 Cancri D, is particularly intriguing. Its immense gravity likely played a role in sculpting the entire system during its violent early history, perhaps hurling smaller bodies inward or stabilizing the orbits of its sibling worlds. The diamond planet, in its hellish orbit, is just one piece of this grand puzzle, a testament to the chaotic and creative processes that can build entire families of worlds around a single star. 41 light-years is a distance that defies human intuition. It means the faint starlight we analyze tonight began its journey when many of us were children, carrying with it an imprint of the system from a time decades in our past. This staggering distance places a fundamental barrier between us and 55 Cancri E. We will never receive a postcard from its surface. No probe will send back a crystal-clear image of its glittering plains or molten seas, at least not for centuries. Every single detail we have discussed, from its diamond heart to its possible carbon crust, has been pieced together without ever directly seeing the planet itself. This is the brilliant, inferential puzzle of modern exoplanet science. Our knowledge is built entirely on shadows and whispers. The primary tools are 2 indirect, yet astonishingly powerful methods. The first is the transit. As the planet passes in front of its star from our vantage point, it blocks a minuscule fraction of the starlight. That tiny, periodic dip in brightness tells us the planet's size. But scientists can go further. By analyzing the starlight that filters through the razor-thin rim of the planet's atmosphere during these transits, they can search for the chemical fingerprints of gases, like a forensic analyst studying light passed through a distant smog. The second method is the radial velocity wobble we discussed earlier, feeling the star's subtle dance to weigh the planet. All our models of its interior, all our talk of diamond mantles and iron cores, are sophisticated solutions to a mathematical equation built on just a few numbers: mass, radius, and stellar chemistry. We are, in effect, blindfolded geologists deducing the entire structure of a world by listening to the echo of its footsteps and weighing the shadow it casts. This indirect reality makes every confident statement about 55 Cancri a triumph of human ingenuity. It is a reminder that our understanding of the cosmos is often a story of clever deduction, of connecting dots separated by light years to reveal a picture hidden in plain sight. But a hypothesis this dazzling must withstand intense scrutiny. The diamond planet model is compelling, but in science, every extraordinary claim demands that we ask the hard question: could it be something else? The answer is yes, and exploring these alternatives reveals the careful, sometimes messy, process of discovery. One prominent counter-proposal argues that we might be overestimating the diamond. This model suggests that 55 Cancri is fundamentally a lava world, much like our initial simpler assumptions, but with a twist. Its interior could be dominated by silicates, the rocky materials common in our solar system, yet its crust and upper layers are exceptionally enriched with carbon. In this scenario, the planet might have a graphite surface floating atop a global magma ocean, with only a relatively thin layer of diamond forming at the boundary where the carbon-rich crust meets the immense pressures below. It would still be a world touched by diamond, but not one built around a heart of solid gemstone. The high density could be explained by other, less exotic heavy elements mixed deeply into the mantle. Another, even more radical idea floats the possibility of a supercritical water layer. At the extreme temperatures and pressures on this world, water would not exist as a liquid, a vapor, or ice. It would enter a fourth, supercritical state, a bizarre fluid gas hybrid with the density of a liquid but the ability to diffuse through solids like a gas. Some models show that a thick envelope of this supercritical water, mixed with dissolved silicates and gases, could potentially account for the planet's observed mass and radius without requiring a diamond interior at all. These competing ideas are not weaknesses in the story, they are its strength. They represent the essential back and forth of scientific progress. Each model makes specific predictions. The diamond-rich world would have a very specific heat signature and lack certain atmospheric molecules. The supercritical water world might exhibit hints of water vapor or oxygen compounds in a tenuous haze. As the James Webb Space Telescope and other instruments gather more precise data, they will test these predictions against reality. The diamond hypothesis currently fits the known facts most elegantly, but science remains always open to a better explanation. This intellectual tension is what pushes our understanding forward, ensuring that what we accept as truth is not just a beautiful story, but the one that best survives the relentless interrogation of the cosmos itself. This cosmic jewel forces a profound shift in perspective. For centuries, our only blueprint for a solar system was the one outside our window, a yellow star orbited by a tidy arrangement of rocky inner planets and gaseous outer giants. This was the template we carried with us into the galaxy, the standard against which we measured every new discovery. The diamond planet shatters that template completely. It proves that our solar system is not the default, but merely one possible outcome of cosmic construction. The universe, it turns out, is a far more inventive architect. If a star's recipe is rich in carbon, it can forge worlds from graphite and silicon carbide. If it is rich in iron, models suggest it could create a planet with a surface of solid metal. Around other stars, we may find worlds of pure water ice or globes of searing hot lava with no solid surface at all. Our familiar categories of rocky and gaseous are just the beginning of a much stranger catalogue. This realization expands our imagination in a fundamental way. It asks us to let go of an Earth-centric view and accept that nature's palette for planet building is vaster and more exotic than we ever dreamed. Every strange new world we find rewrites the rules, teaching us that what seems impossible here might be commonplace elsewhere. This intellectual liberation is thrilling, but it also carries a sobering implication for the search for life. A carbon-rich super-Earth like 55 Cancri e, for all its dazzling beauty, is almost certainly sterile. The very chemistry that creates its diamond heart makes it hostile to life as we understand it. Life on Earth is built on a foundation of carbon, yes, but it operates within a solvent of water and relies on a vast network of chemical reactions involving oxygen, nitrogen, and phosphorus. On a world where carbon is so abundant it crystallizes into planetary layers, the delicate balance needed for biochemistry is impossible. The surface is either molten rock or a brittle carbon crust bathed in lethal radiation, with no stable liquid water or breathable atmosphere. Such worlds are geological marvels, but they are not cradles. This understanding, however, sharpens our search. By learning to identify these exotic, lifeless planets, we can better recognize the ones that are not. We can focus our efforts on stars with more Earth-like chemistry, on worlds orbiting in temperate zones, on places where the ingredients for life as we know it might have had a chance to simmer and combine. The diamond planet, in its silent, blazing orbit, serves as a brilliant guidepost. It shows us one extreme path planet formation can take, so we can better appreciate the rare and delicate conditions that led to our own pale blue dot. Its existence makes our living world seem not ordinary, but infinitely more precious. The future of this cosmic investigation shines with promise, as new generations of telescopes are being designed to see further and with sharper eyes than ever before. While the James Webb Space Telescope is currently our most powerful tool, the plans already on the drawing board aim to push the boundaries of what we can learn about worlds like 55 Cancri e. One of the most ambitious concepts is NASA's proposed Habitable Worlds Observatory. This mission is envisioned as a direct successor to Webb and Hubble, a giant space telescope specifically engineered to hunt for signs of life on planets around other stars. While its primary goal is to study Earth-like worlds in habitable zones, its extraordinary sensitivity will also revolutionize our study of extreme planets. For a world like 55 Cancri e, the Habitable Worlds Observatory could perform spectroscopy of staggering clarity. It might be able to distinguish not just the presence of carbon monoxide in a wispy atmosphere, but map where those molecules are concentrated across the planet's dayside and nightside. This would give us our first crude weather map of an alien world, showing how gases circulate or fail to circulate between its blistering and frozen hemispheres. Even more tantalizing is the potential of advanced direct imaging missions, concepts that use sophisticated starshades or coronagraphs to physically block the blinding light of the parent star. Imagine a telescope so precise it can blot out the glare of 55 Cancri a, allowing the faint, warm glow of the planet itself to be seen as a distinct tiny dot. From that single point of light, scientists could extract a treasure trove of information. By analyzing how that dot brightens and dims as the planet rotates, we could create a detailed temperature map. We might see the precise boundary of the permanent lava ocean, watch the searing hotspot of the substellar point, and measure the profound cold of the dark side. This data could finally settle the debate about an atmosphere by revealing its exact thickness and global structure. Further into the future, even larger arrays of telescopes in space could attempt the ultimate feat, detecting light reflected directly from the planet's surface. While we will never see a detailed photograph, subtle variations in color and brightness across that rotating dot could hint at surface composition. A slightly darker region might suggest a vast plain of graphite, while a glint of different mineralogy could indicate where silicon carbide mountains pierce a molten sea. Each new mission brings us one step closer to transforming 55 Cancri E from a collection of mathematical inferences and spectral lines into a world we can almost visualize. We are moving from simply knowing it exists to beginning to understand its geography, its meteorology, and the profound geology of its hidden heart. The diamond planet, a symbol of extreme and alien formation, will remain a prime target, a testing ground for our technology and our imagination as we reach for the next frontier in seeing the unseen. This stark difference between worlds begins with the very dust from which they were born. Our Earth is a child of an oxygen-rich nebula. When our sun ignited, the swirling disk of gas and dust that surrounded it had a specific chemical recipe, one where oxygen atoms were plentiful. This meant that as microscopic particles collided and stuck together, they naturally formed silicates, compounds of silicon and oxygen. These are the fundamental building blocks of all the rocky planets in our solar system. Think of common sand or the granite of a mountain or the basalt of an ocean floor. That is the geology of our world, forged from an oxygen-dominated pantry. Earth's structure reflects this. We have a dense core of iron and nickel, a thick mantle of silicate rock that slowly churns over eons, and a thin crust of lighter silicate minerals. Our atmosphere and vast oceans came later, delivered by icy comets and asteroids, but the planet's solid body is fundamentally a ball of rock and metal. This is the familiar template, the one we assumed might be universal. Then we found 55 Cancri E, and the template shattered. That world formed from a cosmic kitchen stocked with entirely different ingredients. Its primordial disk was carbon-rich. In that environment, carbon atoms were the most available building material. Instead of silicon eagerly bonding with oxygen to make rock, carbon bonded with itself and with other elements like silicon and iron. So the first solid grains that clumped together in that distant disk were not flecks of silicate dust, but particles of graphite and carbides. Imagine the difference between a sculptor starting with clay versus starting with pure graphite. The final statue will have a completely different nature, color, and strength. This simple shift in stellar chemistry cascades through the entire process of planet formation. The snowline, the distance from the star where water and other volatiles can freeze, is different in a carbon-rich system. The types of asteroids and planetesimals that form are alien. Everything from the core to the potential atmosphere is built from a carbon-based blueprint. This is the core principle of comparative planetology. By placing Earth and 55 Cancri E side by side, we see a powerful demonstration of a universal rule. A planet is a direct reflection of its star's composition. You cannot get a silicate rocky world from a carbon-rich star, just as you cannot grow an oak tree from a packet of tomato seeds. The initial conditions set by that swirling cloud of stellar nursery material dictate the entire future of the planetary system. It determines what minerals will be common, what the surfaces will be made of, and even what kinds of atmospheres might cling to those worlds. Our solar system gave us a geology of mountains, canyons, and oceans. The 55 Cancri system gave us a geology of graphite plains, silicon carbide peaks, and a deep layer of crystalline carbon. Both are natural outcomes, both are logical. They simply started with a different set of instructions written in the atoms of their newborn suns. This realization transforms how we see the galaxy. We are not looking for copies of home. We are learning to read the chemical signatures of distant stars and from that alone begin to imagine the utterly foreign landscapes of the worlds that must orbit them. The story of a diamond planet did not stay confined to scientific journals. It ignited a firestorm in the public imagination, becoming a cultural phenomenon in its own right. Headlines screamed about the world worth $26 nonillion, a number so vast it became a meme, a shorthand for unimaginable cosmic wealth. The idea captured something primal in us, a mix of genuine scientific awe and a deeply human fascination with material treasure. It is a perfect storm, a discovery that stretches our understanding of the universe, yet frames that wonder in a language of value we instinctively understand. This planet became a star in documentaries and a plot point in science fiction, often portrayed as a glittering sphere of pure gemstone floating serenely in space. These portrayals are, of course, dramatic oversimplifications. They skip the hellish lava oceans, the crushing pressures, and the dark graphite plains to focus on the single, dazzling element of the story. Yet, this simplification serves a vital purpose. It acts as a gateway. That initial, irresistible hook of a diamond planet draws people in, making them curious about the real science behind the sensational headline. It transforms an obscure exoplanet with a catalog number into a character in a cosmic story, one people want to understand. In this way, media portrayals, even when slightly inaccurate, perform a crucial act of translation. They take complex astrophysical models and render them into a narrative of discovery and wonder that anyone can grasp. They remind us that science is not just about data points, but about the stories we tell about our place in a universe capable of such astonishing creations. That staggering non-alien-dollar price tag forces a more practical question onto the stage. If we cannot mine a diamond world 41 light-years away, what about the resources within our own cosmic backyard? The fantasy of 55 Cancri E collides with the emerging reality of space resource utilization. Our solar system is not filled with diamond planets, but it is rich with other treasures. Near-Earth asteroids, for instance, are floating mountains of metal and minerals. Some are thought to be packed with platinum, iridium, and other rare Earth elements crucial for modern technology. The Moon's soil contains helium-3, a potential fuel for future fusion reactors. Water ice locked in the shadows of lunar craters or within asteroids could be split into hydrogen and oxygen, the very rocket fuel needed to explore deeper space. This is not science fiction. Multiple companies and national space agencies are actively developing the technology to prospect, extract, and process these off-world materials. The goal is not to bring back a trillion-dollar diamond, but to enable a sustainable human presence beyond Earth. Imagine a future where a spacecraft bound for Mars refuels at a lunar depot, using propellant mined from the Moon's own resources. Or where the materials to build a space station are sourced from an asteroid, saving the immense cost of launching every single bolt and panel from our planet's deep gravity well. This is the pragmatic vision of space mining, using what is already out there to build a future out there. It transforms resources from a payload into a tool, a key that unlocks the next chapter of human exploration. But with this immense potential comes a profound responsibility and a tangle of ethical questions we are only beginning to untangle. Despite the wealth of data, 55 Cancri E guards its deepest secrets with stubborn resolve. The most immediate puzzle is the true state of its surface. Is it a global, churning ocean of molten rock, or does it have solid, if bizarre, continents of graphite and silicon carbide? Measurements of its thermal emission show a massive temperature difference, but that could be explained by either scenario. A solid surface with no atmosphere would also show extreme contrast. Some models even suggest a hybrid reality, a molten dacite constantly evaporating into a thin, transient vapor that rains down as carbon snow on the frozen night side. We simply do not have the resolution yet to map its geology directly. Closely tied to this is the enduring mystery of its atmosphere or lack thereof. The detection of potential molecules like hydrogen cyanide was tantalizing but not yet definitive. If an atmosphere exists, is it a uniform, thin shroud, or is it localized solely over the searing lava ocean, perpetually boiling off and replenishing itself? Or has the star's fury stripped it completely bare, leaving the planet exposed to the vacuum? each possibility paints a dramatically different picture of its day-to-day, or rather, its minute-to-minute reality. Then there is the grand question of its interior crystal structure. We speak confidently of a diamond mantle, but diamond itself can have different atomic arrangements under different pressures. The carbon deep within 55 Cancri E might be in a form scientists call non-stellate, or another high-pressure phase we have not even discovered in laboratories. Is it a single, monstrous crystal or a polycrystalline mass? And what is the precise boundary between the graphite crust, the diamond mantle, and the metallic core? Our models provide a range of plausible structures, but the exact blueprint remains hidden beneath thousands of miles of alien material. This leads to the ultimate summarizing question: is 55 Cancri truly a diamond planet, or is it fundamentally a graphite world with a diamond lining? The distinction is more than semantic, it speaks to its very formation. A planet with a diamond heart suggests carbon was a primary building block from its core outward. A world with a thick graphite crust and a thinner diamond layer might imply a different history, perhaps one where carbon was delivered later or enriched only the upper layers. Every new observation from telescopes like James Webb is a vote for one of these competing visions. This world is not a solved case, but an active crime scene, with astronomers as detectives sifting through the evidence. Each new spectrum, each refined temperature measurement, forces us to adjust the model, bringing us closer to a truth that is undoubtedly stranger than any single headline. The story of the diamond planet is still being written, one photon of starlight at a time. From a subtle stellar wobble to a world of unimaginable extremes, the story of 55 Cancri E is a masterclass in cosmic deduction. We began with a puzzling density, then traced that clue back to a carbon-rich star, which led to a radical hypothesis. This wasn't a planet built like our own, but a world forged from graphite and silicon carbide, with a heart potentially crystallized into diamond. We confronted its hellish reality of tidal locking and searing lava oceans, and saw how evidence from Spitzer and Hubble, measuring heat and hunting for atmospheres, slowly built the case. Yet for all we've inferred, the deepest mysteries remain. The exact structure of its interior, the true nature of its surface, and the final word on its fleeting atmosphere are still written in starlight we are only now learning to read. This journey reveals more than the possible existence of a single diamond world. It fundamentally reshapes our understanding of what a planet can be. Our solar system, with its rocky inner worlds and gaseous giants, is just one possible arrangement in a vast cosmic catalogue. 55 Cancri E stands as a brilliant testament to the universe's boundless creativity, proving that with a different stellar recipe, entirely new geology's worlds of tar, of metal, of gemstone can spring into being. These discoveries do more than fill astronomy textbooks. They stretch the canvas of our imagination. They remind us that reality, when viewed on a galactic scale, is consistently more astonishing than our wildest fiction. Every strange new world we find is a lesson in cosmic humility and wonder, proving that the universe is not only stranger than we suppose, but stranger than we can suppose. What does the existence of such a distant, glittering enigma make you wonder about our place in the cosmos? Share your thoughts on this cosmic jewel below, and subscribe to join us as we continue unraveling the deepest mysteries of space.